Hello everyone. In this video, we'll build a UART controller in Verilog that lets us send MNIST images from a computer to an FPGA. We're doing this because later in this series, we'll run a neural network on the FPGA to classify those images in real time. But before we can run the network, we first need a reliable way to transfer the images to the FPGA. By the end of this video, you'll have everything you need to send MNIST image data over UART. As a reminder, this video is part 2 of a 7-part video series where we implement artificial intelligence on an FPGA. Across these 7 videos, I'll show you how to deploy a feed-forward neural network onto an FPGA and use it to perform real-time image classification on the MNIST dataset. What you are seeing right now is the end result. Images are being streamed from a computer to the FPGA over UART. The network processes the received images, and the classification output is displayed on the 7-segment display. As a reminder, this channel has 2 Verilog courses, an introductory course and an advanced course. The UART and AI videos are part of the advanced course playlist. To find it, just go to the channel and click on the advanced course playlist. Also note that every video in the advanced playlist is based on this textbook. This book contains detailed examples of every possible RTL problem that you would be expected to solve in industry. It has sections on control, on communication protocols, on signal processing, and more. If your goal is to become an expert in Verilog-based design in the shortest amount of time possible, then buying this book is a wise investment. The links to buy the book are in the video description. Alright, let's get started. UART is serial, so we send an MNIST image 1 pixel at a time. That requires flattening the 28 by 28 image into a 784 element long vector, as shown below. Once we have the flattened 784 element vector, we represent each pixel as a 32-bit value. Since UART transmits 1 byte at a time, each pixel is sent as 4 consecutive bytes. That means that each image requires 3,136 bytes on the RX line. The animation below shows how pixels are sent out. At the start, we send out pixel 0 with 4 bytes. Then, we send out pixel 1 with 4 bytes. While not shown, this process would continue until all 784 pixels have been shifted out. In the previous video, we designed a UART receiver. It samples the RX serial stream, assembles each received byte into an 8-bit parallel value, and pulses a done signal when the byte is valid. If you haven't seen that video, I recommend watching it first before continuing. When we stream the 3,136 bytes across the RX line, the UART receiver converts it into the following data stream. Each group of 4 bytes is 1 pixel. The end goal is to get all of the pixels stored in a memory unit, so the main challenge is in transferring the pixels within the stream into memory. To store the pixels from the stream into memory, we must use the 3 modules shown below. The receiver RAM interface takes the input stream from the UART receiver and reformats it into a way that can write into memory. In our example, the receiver RAM interface is designed to accept a burst of 3,136 bytes. Every 4 consecutive bytes are concatenated to form one 32-bit word, which is written to the current memory address before the address pointer is incremented. For example, the first 4 bytes are combined into a 32-bit word and stored at address 0. The next 4 bytes form the next 32-bit word stored at address 1, and so on. Once address 783 is written, the address counter wraps back around to 0, so any new burst sent from the computer overwrites the previous data. When making the UART receiver, we must declare the module as shown on lines 3 to 11. Then we must declare registers to store all of the internal values, as shown on lines 13 to 16. The main logic for the receiver RAM interface is shown below. There are 5 states used to implement it. In state 0, we store the first byte. In state 1, we store the second byte. In state 2, we store the third byte. In state 3, the fourth byte arrives, and at that point, we combine all 4 bytes into a 32-bit word, drive the right data bus, assert the right enable for one clock path, and increment the write address. Finally, in state 4, we deassert write enable and return to state 0 so the next group of 4 bytes can be processed. This is the RAM module. It's a standard memory unit, so there's nothing new here, so we won't go into detail. This is the top-level module for the complete design. In this code, we declare the module, define the parameters, declare the internal wires, and instantiate the UART receiver. This is the rest of the top-level module. In this section, we simply instantiate the receiver RAM interface in the RAM and connect the signals between them. This is the test bench waveform for the complete design. As you can see, the behavior is exactly what we expect. The byte stream for the UART receiver is correctly converted into a sequence of write commands that stores the pixels into memory. To verify that the design works correctly, I wrote a Python program that transmits 3,136 bytes over UART. Every group of 4 bytes forms one 32-bit value, and each value corresponds to the number 0 to 783. This allows us to easily verify correctness. If the data read from memory matches the address, then we know that the interface and RAM are functioning properly. The animation below shows the order that each byte is sent serially across the RX line. Remember that each group of 4 bytes forms one pixel. And remember that the groups are sent such that the numbers 0 to 783 are sent in order. Now that I have explained the test setup, let's look at a real demonstration. In this demonstration, I use a Python program to manually send 3,136 bytes out of the RX line at 9600 baud with 1 start bit, 8 data bits, and 2 stop bits. The bytes are sent in the way I described earlier, where each group of 4 bytes corresponds to one 32-bit number. Note that in this demonstration, the slide switches drive the address bus of the memory unit, and the LEDs show the lower 16 bits of the read output. As you can clearly see, the UART receiver correctly received the value sent by the program since each address contains the contents that match the address. That's all for this video, and I'll see you in the next one.